Good evening. My name is Dmitry Volchenkov. I'm from Texas Tech University. I profoundly thank the organizers of the third online nonlinear science conference for inviting me to make a joint talk with Professor Steve Zuch from Texas A&M University on statistical mechanics of long walks in dynamic complex networks. Dynamic complex networks are systems whose network properties evolve in time. Graphs are useful for the network analysis as helping us to answer the fundamental question about relations between the local properties, properties pertaining to a single node, and global properties of the entire graph. And in this context, long walks may serve as a metaphor for interaction chains between the network units. My talk partially follows a discussion in our recent article, Statistical Mechanics of Long Walks in Dynamic Complex Networks, Statistical Arguments for Diversifying Selection, just published in the second volume of the new MTPI Open Access Dynamics Journal. Briefly speaking, I'm going to talk about a graph measure, alternative and inverse to the centrality measure. We call this new measure fugacity, borrowing this term from the grand canonical ensemble in equilibrium statistical mechanics. In our context, fugacity measures a disposition of a node to flee or escape from the network, or the local tendency of the network to expand around or abandon a node, so structural modification. While centrality describes a typical traffic density pattern in the network and features hubs playing the important role for the entire transportation network, fugacity rather describes a traffic congestion pattern featuring the structural bottlenecks in which traffic might be caught in case of a road accident or other uncertain conditions. So with a high probability, the network modification might also occur at the same place of high fugacity, as the network might be rewired and the new connections might be added in order to improve the local transportation situation. Anyway, the centrality and fugacity, the places of high traffic density, like here in the slide, so we show the part of San Francisco road networks. So places of high traffic density, high centrality, and the most congested places, high fugacity, are not the same. The outline of my presentation is as follows. We discuss first the statistical mechanics of very long walks in graphs. On the one hand, infinite walks are possible in finite and even very small graphs, such as those portraying the majority of artificially engineered networking systems and power grids. On the other hand, the statistical ensembles of walks don't require the structure of a backbone graph is random, as it was implicitly assumed in complex network theory concerning asymptotically infinite graphs growing accordingly a preferential attachment approach of accumulated advantage. Graphs in our setting, undergo random structural or edge capacity modifications. We show that the corresponding statistics is of Fermi-Dirac type, featuring nodes of high fugacity, prone to modifications. Fermi-Dirac type statistics is for fermions, actually, electrons in an atom. The entire phenomenon looks like a typical stochastic resonance. Under normal operation, traffic density is mostly concentrated and is around hubs or nodes of high centrality. But if we add noise to the system, it flips the distribution as most traffic get caught in traffic jams at the nodes of high fugacity. Well, interestingly, just to compare it with the complex network theory, in complex network theory, they consider another thermodynamic limit of infinite graphs, right? And capital N to infinity. Graph dynamics, eternal growth, preferential attachment, and they have Bose-Einstein statistics pertinent to the preferential attachment approach, and correspondingly, a Bose-Einstein condensation mechanism featuring a topological phase transition from a rich-get-richer phase, producing random trees, to a winner-take-all phase of a heterogeneous star graph with a single major hub. Okay. So, a little bit more details. To be certain, we will consider and discuss finite connected and directed graph defined by symmetric edges and symmetrics. My choice is predetermined by the use of spectral decomposition in the framework of algebraic graph theory. Algebraic graph theory allows to make explicit calculations of all thermodynamic quantities. So we shall discuss three major Gibbs ensembles of statistical mechanics. Microcanonical ensemble of Volk. So in this microcanonical ensemble, all Volks of the same length n are taken with the same probability. The most important quantity characterizing the entire graph is then its chemical potential. Graph topological entropy, showing how many distinguishable microcanonical Volks arise in the graph per each step in the limit of very long Volks. In the canonical ensemble of Volks, all Volks of the same length starting at the same node of the graph are taken with the same probability. The relevant characteristic of the node in the graph is the energy of the node, quantifying how many distinguishable Volks arise per step in the limit of very long Volks. So it's just energy and chemical potential in fact are very similar quantities, but in microcanonical ensembles, mostly it's related to the entire graph. In canonical ensemble, it's related to a node. So these quantities do not coincide. Energy of the node locally fluctuates around the chemical potential of the graph. And then to describe these fluctuations, we need the third peer, grand canonical ensemble of Volks, which give us the probability of local fluctuations of energy around the chemical potential. Okay, so grand canonical ensemble indeed describes the acquiring or losing nodes in the course of interaction with the environment or other nodes. So initially, or other networks. So initially, it's just an open system, right? Open system where the modification might occur, to the graph might occur, just where we have observed a severe fluctuation of energy around the chemical potential. And where do we observe such a fluctuation? Where the node is loosely connected, not very well integrated in the fabric of this network. So this is the major idea. Okay. Now, just a little bit more details. Microcanonical ensemble of Volks. Well, it's defined by assigning equal probability to every n Volk in the graph, by defining probability for all such Volks, Pn, in Gibbs form, the exponent as the exponent of free energy Fn divided by the Boltzmann temperature. And then we just interpret these quantities, the free energy and Boltzmann temperature. Boltzmann temperature is just the base of the logarithm, basically, right? So just binary logarithms are more convenient for all these calculations for graphs, because then there is a clear connection to physical dimension of space, right? To lattices and to regular graphs. We will discuss it a little bit later. But then free energy is a logarithm, is just a binary logarithm of the number of n Volts. And then I calculate the number of n Volts using the algebraic approach, algebraic graph theory. And well, the trick is that we factor out the maximum eigenvalue of the adjacency matrix. The remaining ratios of the eigenvalues are less than 1. So in power of n, this quantity, the entire sum goes to 0, and I have a very compact expression for the free energy of the graph with respect to long walks in the microcanonical ensemble. The rate, so the free energy grows linearly with n, and the rate of the growth is called graph topological entropy, sorry, the growth rate of the number of distinguishable walks per step. Okay. Now, in the context of statistical mechanics, the graph topological entropy is nothing else but an intensive free energy per step or chemical potential of the graph. Moreover, if we model a chunk of d-dimensional space in a diffusion problem by a lattice or a kappa regular graph in which every node has precisely kappa nearest neighbors, then the cardinality number of the diffusion operator should be 2 to power of d, where d is the dimension of space, and the maximal eigenvalue of an adjacency matrix equals precisely kappa. Then the graph topological entropy or a chemical potential of the graph equals the binary logarithm of the maximal eigenvalue, that is d in case of a triangle right here. And the dimension of, therefore the chemical potential can be considered as the efficient space dimension of the graph. So we can calculate the space dimension as a graph topological entropy, and even for the graphs which are not regular. Simple example, if we consider a triangle, adjacency matrix of the triangle, maximum eigenvalue is 2, space dimension is 1, the binary logarithm of 2. That is just a one-dimensional circuit, right? So that's why actually the binary logarithms are very convenient in all these graph-related calculations. Canonical ensemble of walks. Here we have all nth order walks, all walks of length n starting at the same vertex are taken with equal probabilities. We denote the number of walks anchored at I as kappa, and the nth order degree of the node is kappa to n. Well, the adjacency matrix of the graph then defines a linear dynamical system in the capital N dimensional space. And now we apply the same trick to the nth order degree of the node kappa, defining the local growth rate of the number of distinguishable walks anchored at the vertex energy, epsilon I. This local quantity pertinent to a node does not equal to the chemical potential of the graph indeed. Some nodes are better host of very long walks than others, and therefore one quantity would fluctuate around another. Okay, so but just interestingly, the dynamical system defined by the adjacency matrix generates an infinite set of Markov stochastic processes, random walks, one for every length of walks n. So namely, I just going to normalize this dynamical equation, so to say, right, by kappa to n plus 1 and get a row stochastic transition matrix, which defines me a random walk. It's properly normalized. Well, and the entire set family, infinite family of such random walks define the canonical ensemble of walks in G. Why? Because I can remind you the definition of Gibbs given in 1902. So canonical ensemble represents the possible states of a system in equilibrium that does not evolve over time, even though the underlying system might be in constant motion. Well, how these equilibrium states exist? Because all of them are left eigenvectors of some transition operators in Markov chains. Now, if I consider the the entire family of such Markov chains. So the first order random walk gives me the totally completely isotropic random walks, which are studied in the literature. And there are some intermediate transition operators. And finally, as n goes to infinity, I have basically the rule Bowen random walk, which is ultimately anisotropic, because the nearest neighbor hosting the maximum infinitely long walks, are more preferable to be chosen as the next step in the random walk than others. Okay, so left hand side, left eigenvectors of these transition operators are stationary distributions known as centralities. For instance, for the usual Markov chain for the first order random walk, we have a degree centrality. And for Reuel-Bowen random walk, the stationary distribution is a squared eigenvector centrality. So there are many definitions of centrality. Indeed, we know it. And any centrality could be related somehow to one or another stationary distribution in transition operators of canonical ensembles of walks. Also, we can introduce a direction-dependent graph space dimension tensor. And indeed, it's not a space dimension of the graph topological entropy, but now it's a local characteristic because indeed canonical ensembles related, anchored at the particular nodes. So the dimension of graph, a local dimension of graph, is a direction dependent. Indeed, it's very similar to graph topological entropy, but has these factors, the ratio between the elements of the major eigenvector of left-hand side eigenvector of the transition operator, ui and uj, right? So it's a direction. Okay, right. So grand canonical ensemble. Grand canonical ensemble. The probability to observe a local fluctuation of nodes energy about the free energy of the graph with respect to n walks is defined within the grand canonical ensemble. So we call this probability inverse proportion to the eigenvector centrality of a node in the limit of infinitely long walks as nodes fugacity. Again, in the limit, it has a very nice, elegant formula to calculate it. Just the inverse, basically, of the correspondent element of the major eigenvector of the transition operator. The nodes of not transition operator, but adjacency symmetrics. The nodes of high centrality, well integrated into the graph as a hosting many very long walks, have low fugacity and vice versa. The high fugacity assumes that the node is insufficiently integrated into the graph structure and calls for the local structural modifications in the graph in order to improve the local connectivity or abandon the node. The grand partition function Z amasses fugacity over all nodes in the graph, and the grand canonical potential omega play the role of the free energy with respect to the grand partition function. Now, so this is our fugacity distribution. Fugacity distribution, if you can see, it has a Fermi-Dirac form, typical for fermions in a single particle state I with energy EI, with zero chemical potential capital mu, as a node can leave and enter the graph at no cost. So if you noticed, we actually study the systems of walks in a graph, and our thermodynamics is based on quantities related to walks. Nodes can enter and leave the graph at no cost. The change of mobility patterns in the graph due to the disappearance or deactivation of a node can be described by introduction of entropic pressure and entropic force. We discussed it once upon a time on this conference a couple of years ago. So here we just wanted to illustrate the difference between eigenvector centrality and fugacity. So they are opposite to each other, inverse of each other. So the distribution of relative fugacity of vortices can be considered as a normalized inverse eigenvector centrality. The graph vertices with the inferior growth rate of infinitely long walks appear to be insufficiently integrated into the graph structure, and therefore they might be lost or, on the contrary, acquire new connections in the course of graph structural modifications. So in the right-hand side, we have this membrane graph with colored accordingly according to its nodes fugacity, and you see that the highest fugacity is well, the nodes on at the angles of this membrane has the loosely connected for the entire structure to the entire structure have the highest fugacity. So the idea is that if this membrane graph would evolve, the connections or structural modifications might happen mostly start probably at the nodes of the high fugacity. Okay, so interestingly, a Fermi-Dirac distribution of fugacity also appears as the unique stationary solution of a Fokker-Planck equation describing the continuous time dynamics of distributions subject to the canonical ensemble of walks and the noisy transportation capacity of random edge rewiring in a graph. For keeping calculations simple, we consider the limiting transition operator of the Ruel-Bowen random walks. The continuous time evolution of a probability distribution ρ is then described by a forward Kolmogorov equation supplied with some initial condition. Then the Fokker-Planck equation can be obtained by adding white noise described by the Wiener process of strength beta to the forward Kolmogorov equation that is equivalent to rewriting Kolmogorov equation for the Onsager potential and introducing a corresponding noisy random walk operator that turns back into the Ruel-Bowen walks as the noise strength set to 0. So this is a Fokker-Planck equation. And in fact, the Onsager potential, instead of binary logarithm of the elements of eigenvectors of the edges of symmetrics, we have binary logarithm of this eigenvector times ρ at 2 beta. Beta is the strength of the white noise. In the presence of noise, the Gibbs distribution is the unique stationary distribution satisfying the Fokker-Planck equation. And it takes the form of the Fermi-Dirac fugacity distribution if the strength, noise strength beta equals to 1. So we directly get the same expression as before. If in case of very strong noise, when beta tends to infinity, the stationary solution converges to a uniform distribution over the graph nodes independently of the graph structure. Well, just to give you another example, basically, so this is the Minnesota road network. Eigenvector centrality tells us that in the long run, the traffic density would be anchored to Minneapolis, the capital city of Minnesota. But if we add noise to the graph, then you see that high fugacity, places of high fugacity are dispersed well along the entire road network, and we can expect traffic jams in these places. So there is a situation resembling the story about stochastic resonance. Before, if noise is 0, so if if there is no noise, then the traffic signal, so to say, from all the places in this road network, excepting for Minneapolis itself, is very weak. But then, as soon as we add some noise, then basically we got signals, traffic jams at different places. So in fact, it's a stochastic resonance. Signal that is normally too weak can be boosted by adding white noise to the signal. Well, while central hubs accumulate the most of traffic in normally operating transport network, like Place d'Étoile à Paris, traffic congestion may catch it at the nodes of low centrality and structural bottlenecks due to the random fluctuations of transportation capacity in networks. And then new edges may be added to the network, preferably connecting to the most disadvantageous nodes. It looks essentially like an inverse preferential attachment. We can even develop an algorithm for the growth of networks using this inverse preferential attachment principle. The nodes of highest fugacity are more preferable for the future structural modifications. So the graph grows through its worst places, not the best. Just now, as a concluding remarks and discussion, in complex network theory, the thermodynamic limit of infinitely large graphs was considered, and any functionally relevant structural features of a graph growing unboundedly appear to be asymptotically negligible then. They are fluctuations. So all structural features are fluctuations in complex network theory. And therefore, actually, it's failed ultimately to describe the function of engineering a real-world network. The entire network is viewed as an ever-growing collection of structurally homogeneous random graphs in complex network theory. The famous power law statistics of nodes degree distributions then may result from a superposition of the binomial or Poisson degree distributions typical for random graphs. True scale-free graphs are quite rare. The evolution of complex networks is explained in complex network theory by the preferential attachment mechanism under the spell of Matthew principle of accumulated advantage. The Bose-Einstein condensation mechanism features a topological phase transition from a rich get richer phase to a winner takes all phase. On the contrary, we propose in this dynamic complex network theory, we propose to study the statistical ensembles of very long walks sensitive to graph structure. This approach works well for finite and small graphs where complex network theory was not applicable. The special attention in our work was given to the dynamic complex networks open to random structural modifications. Fugacity of a node quantifies the likelihood of local structural modifications at the node or about the node in the course of network evolution. For describing the time evolution of probability distributions of stochastic processes defined on graphs, we introduced a discrete finite version of the Fokker-Planck equation as the generalization of the Kolmogorov equation for the different values of white noise strengths affecting transportation capacity in the network. Being the unique stationary solution of the derived Fokker-Planck equation, the Gibbs distribution takes the form of Fermi-Dirac distribution. The last remark, which is actually sounds very promising and interesting to me, I would like to discuss graph evolution by natural selection. Since dynamic complex networks are ubiquitous in the real world, including complex biological and ecological systems, their evolution might be described in terms of the theory of evolution, in reference to the process of natural selection. And then it's obvious that complex network theory actually gives us an example of stabilizing selection. The entire node population of a huge graph stabilizes on a particular hub. So complex network theory explains the growth of complex evolving networks in the spirit of preferential attachment approach that makes use of analogy with evolutionary models of stabilizing selection, in which the population mean stabilizes on a particular non-extreme trait during some characteristic time of stabilization. The principle of accumulated advantage and positive feedback resulting in the reproductive success of the average phenotypes are then considered as the major mechanisms limiting the individual variability in the theory of stabilizing selection. And similarly, in complex network theory, we have the Bose-Einstein condensation mechanism driving a phase transition of the network topology from to the appearance of a super hub of the maximal centrality and of the highest fitness, accumulating all branches of the network as the graph grows. Indeed, such a theory, in the context of evolution theory, such an approach is not complete, right? Because it does not explain how other species might evolve. So important type of natural selection which is missing is a diversifying or disruptive selection, describing changes in population genetics favorable to extreme values for a trait over the normative values formed in the course of stabilizing selection. So, and dynamic complex network theory, what we try to sketch for you now, then naturally represents the diversifying selection, favorable to the extreme values for a trait over the normative values. So in the worst places of the network, there is a chance of development of the new network. So we have shown that if a network is open to random structural modifications, or if the transportation capacity is affected by white noise, centrality flips its role in the network dynamics. The nodes of minimal centrality, loosely integrated into the fabric of the node of the network, would most likely feature its structural modifications, and concentrations of walkers in a noisy transportation network under traffic congestion would most likely to occur at the nodes of lowest centrality and in structural bottlenecks characterized by the highest fugacity. Thank you so much for your attention. I would be glad to answer your questions. So stop sharing and end.